Well, my dear students, now we are going to start 31st lecture in the series of mechanics of metal forming. Our lecture is going on upper bound solution and formulation. Last time we discussed the upper bound formulation and few examples was taken. And then we took a very generalized example which is valid for 3-dimensional upper bound formulation. So today in this lecture we will consider the 3-dimensional upper bound solution for re-entry shape. Last time we took it for non-re-entry shape and all formulation we did. So now this formulation non-re-entry shape can be used for any other re-entry shape. It can be extended for any other re-entry shape. So let us see how we are going to do it. So before that, the last time whatever we covered, these 3 references can be looked into. One can refer these references for more details. So specifically number 1, the work of Dr. Dikshit, G.K. Lal and Dr. Reddy. The second one, the Professor G.K. Lal, Kripa Shankar and S. Kumar, and the third one also by the same authors. Specifically the second reference which was published in 1999, and then subsequently the analysis part which was published in ASME in 2002. So these 2 are to be referred for more details. So now let us start with application for re-entry component shape. Application of the proposed upper bound model which was demonstrated last time for a general re-entry shape. One can go back and one can see this figure 1 where the H shape is shown, and H shape or L shape, these all falls in the category of your re-entry shape, and the following steps we would be following. It will be carried out for the given re-entry shape to find the process parameters such as optimal power, average extrusion pressure and optimal die length, etc. So let us start. What would be the step? As I told you that the step would be quite similar. Last time we discussed for non-re-entry shape, because the re-entry shape calculation is specifically for optimum power, average extrusion pressure and die length, etc. is concerned from the concept which was proposed in the last lecture corresponding to a non-re-entry shape. So then step 1 is that, as usual, here also the geometry of the re-entry component which is to be extruded is drawn using AutoCAD. One can choose any other package as well. The drawn component is then broken into minimum number of sub components such that each of them represent a non-reentry component shape, and which is shown here in the figure. So this division of a reentry shape into minimum number of non-reentry shape is compulsory, and this is what is the beauty of this work. So the selection of the entities to change the component drawing for this purpose should be made in such a way that each proposed non-reentry shape is separate and unambiguous. The designer should therefore try to propose those non-reentry shape for the reentry shape that could form exactly two or more similar non-reentry shapes, because extra entities that are required to create the proposed non-reentry shapes should be recorded carefully. That is also very important. The note of this extra entry shape are to be taken care, because these entities are extra and it is not to require the frictional power computation specifically for those extra entities. So care should be taken that the frictional power is calculated only once for entities of the reentry shape. Second step is, you can look into here, this is what is given shown here, the proposed segment of the shape which is given here. So you can see where this reentry shape, and it is divided into corresponding non-reentry shape. So there are, and this division has been shown, that is initially the reentry shape is only one piece, but after division it has become three non-reentry shape. So one can see here, and now you see the joints are the extra entities, so it should not be repeated. So the proposed non-reentry shape corresponding to this reentry shape are shown here on the right side. So for an example, and for each such non-reentry shape, the billet diameter is required for specifically for this case as the diameter D1, D2 and D3. So but now we require 3 diameter, whereas if it is only 1, then the diameter was 0, D0. That means if I take the whole as a corresponding diameter, it should match with D0. So that's how a condition, that is the has to satisfy that D0 is square must be equal to D1 is square plus D2 is square plus D3 is square, because there are 3 diameters here now based on the 3 corresponding non-reentry shape. So this sequence, this process are to be very carefully noted, and extra entities like the here, if you look at here, there are 1, 2 and 3 extra entities. So that should be noted, and it should not be there while calculating the frictional power calculation corresponding to these entities, it should not be repeated. So this point has to be marked very carefully. So the second step is that for the center of gravity and the cross sectional area, that is capital AA, for each proposed non-reentry shape, is 3 in this case especially, is found using either simple calculation, or one can also use AutoCAD for, that is the advanced modeling extension can also be used of AutoCAD, or somehow else can also be calculated. Once the CG is calculated and capital AA corresponding to all these shapes are calculated, Then the third step is that separate the DXF file for corresponding to these three shapes. Separate DXF file is created for each proposed non-reentry shape, which is mentioned in step 1. Each of them is processed separately to extract line and arc entities as explained earlier lecture. Number 4th step is that each of the proposed non-reentry shape, which was mentioned in step 2, is treated separately, and step 3 to 9 are followed as explained in this section that we are going to just now deliver, to calculate the individual optimal power, that is psi minimum, and the optimum die length, that is L opt. And one can use the golden section unimodal optimization algorithm as suggested last time. The fifth step is that let there be n bar number of non-reentry shapes proposed for a given reentry shape. So specifically for this case it is n bar is 3, where n bar represents 1, 2, 3 and depending on the proposed reentry shape. And then you find out for each, you find out the center of gravity and cross sectional area capital AA for each such non-reentry shape, and that is what has been shown earlier step 2. So for the required reduction, so the total, suppose the total reduction is something is given, say, so separate billets for each of the proposed non-reentry shape should be obtained. As I mentioned, now for this case the billets diameter would be D1, D2 and D3, and it has to satisfy that D0 square is equal to D1 square plus D2 square plus D3 square. So the diameter of nth billet can be found out as this formula. So nth billet is found out under root 4 by pi capital A by A square divided by 1 minus 0.01 reduction, whatever reduction is there. So if you use this, one can find out the diameter of nth billet. So and the corresponding capital AA, that is capital AAN. So would be the required billet diameter and cross sectional area of the nth proposed non-reentry shape. So this is what the fifth step. And for an example, let psi opt n bar and L opt n bar be the optimal power and optimal die length for the nth proposed non-reentry shape. So with increase in friction conditions, the optimal die length, that is L opt n bar, will reduce, and whereas the corresponding optimal power, that is psi opt n bar, will increase. This is quite obvious. So in the sixth step, what we will do, the minimum overall power, that is phi O optimal, and the minimum billet diameter, that is D0, for the re-entry shape, if you recall the step 1, can be then found out. As I told you, phi 0 would be phi 1 opt plus phi 2 opt plus phi 3 opt, likewise phi n bar opt, and similarly D0 would be under root D1 square plus D2 square plus D3 square and so on plus d n bar square. And similarly the average ram pressure, that is P average, would be calculated as phi O divided by pi r square V0, and then one can calculate the relative extrusion pressure, that is RL, as P average by sigma 0. That is the simple step. And in the last step, that is 7th step, the overall optimal dye length, that is L opt, for the re-entry shape is decided on the basis of power phi 0, phi o, using golden section optimization technique, as I told, for the proposed non-re-entry shape of the re-entry shape. The relative optimum dye length is evaluated as capital RL, and that is L opt by R0. If all the proposed non-re-entry shape are of symmetrical in nature, so similar profiles and the cross sectional area in terms of, so in that case individual dye length, that is capital L, is same for all the proposed non-re-entry shape, and it is equal to the L opt therefore. This point is to be noted. The values and different, these values are different when the proposed non-re-entry shape are non-symmetrical in nature. For a non-symmetrical re-entry shape, individual values of capital L for each non-re-entry shape is taken as L, which is equal to 2L opt by D0. This kind of assignment of optimal dye length for the proposed non-symmetrical non-re-entry shape simplifies the solution without much loss in the accuracy of the result. In case of symmetrical shapes, however, exact solution is required. This is very important. So this 7-step process is a generalized one, and in this flow chart the same thing has been shown. The flow chart is in two parts. This is the first part, first half of the flow chart. One can see it starts, and then the number of proposed feature data and the center of gravity capital A and other things are noted, and then it is initialize the step as 0th step, and then normalize the feature data of the shape with separate for separating the and finding out the center of gravity of the feature. Feature concept, one can refer the second reference as I propose. The feature concept is a the whole shape is proposed as a one feature. Suppose there is a multi-die, multi-extrusion, multi-hole extrusion, then there would be many features. So that is how the feature concept has been brought into. So if however there is a single hole extrusion, then there is only one feature, but when there is a multi-die hole and multi products are being extruded simultaneously, in that case this becomes much more important. So this step, using the step which was proposed, you first find out all the your proposed non-re-entry shape corresponding to a re-entry shape, and then you for then slicing etc. as told, and check the incompressibility for each case, and once the incompressibility is satisfied, then it gives the valid number of power element data for extrusion die design, and then other input like die friction conditions, the extrusion ratio, input velocity of the RAM, then the reduction, then the contraction, optimum die length, all those things are also required to give. So otherwise the numerical modifications are required to the geometry as told earlier, and then then it goes to the initializing the power, and you find out the power. So you take the first power element and find the total power this for the element. So this is shown here in flow chart. So this is what is the for the whole upper bound methodology for re-entry shape is explained, and it is quite clear that at the stage when the everything is satisfied, then one can stop at the end here. If it is not satisfied, then you go back to the iterations, and again according to the conditions which has been shown here, one have to follow. So after it has been found that after 5-6 step for each such non-reentry shape, the optimization comes into and solution is achieved. So one should be, however, very much careful that again to remind that the entity should not be repeated. That is, the power specifically for the frictional case for those elements would not be repeated. Otherwise, there would be a mistake, slight mistake. So this is what is the process. Now let us take some of the examples to illustrate the work. That means this proposed methodology for re-entry shape, one has to ensure that it is correct. So Young ETL, Young and their group in 1990 conducted lot of experiment for non-axis symmetric extrusion of rounded square and clover section, and it was, if you recall it back, that was also discussed that time. So these examples are again solved by the procedure which is now considered and explained for re-entry shape. So if it is proposed as a re-entry shape, that means a square and clover section, and if you follow this procedure, let us see we get the same result or not as we did it for non-re-entry shape. The details of the material specification and other process parameter are all taken the same as it was given in the previous lecture. So Young and group, so 1990 paper. So let us see how we are going to start with. So look at this figure. So this is the square section and this is another clover section. So the geometrical construction as far as is concerned, so you look at this one. The first one is your square section, which is a non-re-entry shape, and the second one is a clover section, it is non-re-entry, but we would solve it with the methodology that was discussed for re-entry shape. So how we can do? So here is the second column of the table. So this is divided into two, the square is divided into 2 and the clover is divided into 5 such. If it is assumed as re-entry, then it is further classified into 5 such non-re-entry shape. So you will see the number 1 is one number and number 4 are symmetrical, 4 numbers, that is the item 2 is 4 number. So that's how the, and in for the square there are 2, so one number and one number 2, and one can calculate the initial cross section and the individual cross section. So initially it was 273.5 mm square, but when we break it out in 2 pieces, the area is become, if we want to reduce it for 60% reduction, then it is 14.75. So this is what the diameter. So the required billet diameter is 14.75 and the reduction is 60%. Similarly, for the clover section, the 273.397 was the cross sectional area and the required billet diameter is again 14.75 for the 60% reduction. Please note that these two are symmetric. These two cases are symmetric. So the initial geometrical details of rounded square and the clover sections are also taken as explained earlier in the Young 90s work. Their cross-sectional profiles are drawn accurately on true scale using AutoCAD and following the steps proposed earlier for as just now for re-entry shape procedure. Rounded square and clover sections are broken into 2 and 5 non-re-entry shapes as I told separately. So for all these shapes, separate DXF files are created and pre-processed to separate the geometrical data as explained earlier. So minimum number of pseudo vertices, that is NS, that is a minimum power element for individual sub shapes are generated using this table. The results obtained for these two cases are compared, one can see in the next table here, with the experimental result which was proposed by Young et al. In 1990. The another work of Young, the result clearly shows, it has been observed that the result shows that the extracting the non-re-entry solution methodology for, because we are using the same methodology that we are going to extend it. So the extending the non-re-entry solution methodology for re-entry shape does not compromise on accuracy and there is no difference in splitting the re-entry shape into 2 or more non-re-entry shapes. Results that we are going to show you, it clearly shows that the same result is obtained for all symmetric re-entry shapes and for non-re-entry shape, however, accuracy will get affected. So this is what is the table after. So one can see here that the total number of power elements for the square one is 472, total number of power element, whereas it for the clover section it is 4 multiplied by 40, that plus 42, that means it is 202 power elements. Now when we get using the steps that we have proposed, so if we calculate the extrusion power and if we calculate the ram pressure, so for the square section the extrusion power is calculated as 236.8 watt and the corresponding ram pressure comes out to be 346.455 megapascal, whereas for the clover section the total power is total 285.83 watt and the pressure, extrusion pressure comes out to be 418.2 megapascal. The proposed optimum die length in mm for the square section is found to be 29.555 and similarly for the clover also it is found to be 29.55. So this is what the result shows, that the things are, there is no harm in splitting the re-entry shape into minimum number of non-reentry shape and then following the same procedure of the upper bound and getting the power and optimum, there is no harm, it is proved then. That is the beauty. So, using this step, using this procedure, let us take another example of this H shape. So, H shape is very popular example of a re-entry shape, and it's basically this shape having this particular dimension shown. The Q-Chi and his research worker, they proposed some work in 1980 work, and they demonstrated an analytical method to calculate the power and extrusion pressure at optimal die length for extrusion of various kinds of re-entry, that is non-symmetric cross sections, such as square, such as rectangle, hexagon, L shape, T shape, H shape, etc. So, various results and trends obtained by them have been claimed to be of very acceptable range. So, however, these results have not been validated with experiment. So, therefore, we have chosen this H shape, a re-entry shape, to validate the trend obtained by the Q-Chi 81 work, because they have already, they are using their own analytical method, they got some trend of forming. So, therefore, if you apply for this shape, the shape is broken, is taken to study the relationship between relative die length and the relative stress using a conical die, because they also use conical die. So, here also we are taking a chemical die for the study. So, details of the material specification as far as concerned and other process parameter for this study are taken as same as the Q-Chi 81 has taken. So, the material property is as far as was taken as steel, that is AISI 4140 steel, and with the stress strain relationship as shown here, that is 418.9 plus 699 strain, generalized strain rate to the power 0.266 megapascal. The billet radius was taken as 40.8 mm. Die profile was taken as conical die profile, and therefore we are also choosing, and they in their analysis also Q-Chi, they use some other upper bound solution for these all these shapes as I told you, and the ram pressure whatever they choose was 1 mm per second. The temperature, obviously it is room temperature taken as 20 degrees centigrade, and as far as the geometrical construction is concerned, the initial geometrical details of S section is taken from the Q-Chi's work. So, that means their cross sectional profiles are drawn accurately using AutoCAD, and following the steps as just now I proposed for the re-entry shape is taken. The shape is broken into two such shapes which is shown here for this particular H shape, and corresponding DXF file are created and pre-processed to separate the geometrical data as explained. The minimum number of pseudo vertices, that is the minimum power elements for individual sub shapes, are generated as it was also shown in flow chart, and the minimum number of power elements is generated on the basis of this particular table. So, look at the trend obtained here. This is what the segmentation is shown. that is means H shape is segmented in two shapes which is quite symmetric in fact. So, you need to calculate the power for only one, the overall power for one, and then multiply it by 2 the total power, and then divided by pi r square V0 to get the extrusion pressure for the whole H shape. So, this trend, when the study was carried out, this trend is obtained, that is the relative die length and the relative stress obtained here. So, one can see for the reduction as 55%, 60% and 70% it has been observed. So, this reduction, this result for different reductions, when it is compared with the Kyuchi's work, it is seen that the trend obtained by the proposed methodology for re-entry shape is very similar to that which was obtained by Kyuchi et al. In 1981. So, this is a very good satisfaction rather, that the methodology still works. So, let us take another example here. We are taking many such other shapes, and let us take these 8 commonly used re-entry shape along with the details of the cross sectional area and the initial billet area which would be required using this methodology, the one we discussed in the. So, these shapes are chosen to demonstrate the result obtained by the proposed upper bound methodology for re-entry shape. Geometrical details of the shape have been taken from various sources. Details of the material specification and other process parameters for the analytical experiment are given here. One can see the material is again steel is chosen, AISI, same as the Kyuchi's. The billet diameter is 40, radius is 40 mm, die profile is third order, ram velocity is 1 mm per second, friction condition is 0.1 and temperature as room temperature is taken. So, the geometrical construction as far as is concerned, it is all these shapes, the rounded square and the clover sections are taken from the previous example. The other cross sectional profiles are drawn accurately similarly as explained earlier on in AutoCAD, and then the following the steps which was proposed, the shape, the DXF file is created and the data is processed out of the DXF file, and then the minimum number of pseudo vertices are proposed, and then the minimum number of power elements for each such shapes are generated, and this is what is and be shown in this table. So, minimum number of power elements generated on the basis of this table are used for overall power calculation, and the predicted results obtained using this particular upper bound solution procedure is shown in the next table. So, you look at this. So, there are 1, 2, 3, 4 such different shapes, re-entry shape, one can see, very complicated. The third one is the same as the H1 we discussed, and the proposed re-entry segmentation shapes are shown here in the third column. One can see how the things are broken up. The fourth one is of interest, where 1, 2, 3, 4, 5, 6, 7, 8. There are 8 leaps like. So, the corresponding has a round one and the only one. So, you have to calculate only for 2, because there are shape number 1 is 8 numbers and 2 is 1 number. So, the cross sectional area and for each such shape, the diameter of the billet and the percentage reduction is shown here, and whether it is a symmetric or non-symmetric is shown. For an example, case 1 is a non-symmetric, and case 3 and 4 is symmetric. Then this again the same table, the 5, 6, 7, 8, 4 more examples are taken. These examples are very popular examples. So again here the workout has been done to break out into the corresponding non-reentry shape, number of non-reentry shape for these figures, and all those things has been calculated. So this is the result. This table shows the result of these using the upper bound proposed. So one can see here, say for the example case 1, the total number of power elements are 210, 2 is 210, 3 is 292, 4 is 647. When you propose the power and pressure, it is also shown here. So for an example, for case 1 the power is 1687.42 watt and the pressure is 2607.47 megapascal, and the proposed optimum die length comes out to be 29.36. The case 4 on the other hand, the power is 2387 watt and the pressure is 13,332.39 megapascal, and the optimal die length is 47.30. So that's the beauty, and this result showed absolutely correct values. One can try with doing experiment for this shape and finding out these results which is proposed. We have done on the later side, we have seen that whatever result it is shown here, it is absolutely correct. Even after we did experiment later also, and we have found that this is correct. So this further validates the proposed method, and therefore one has to practice it. So this method for re-entry shape, that is upper bound solution, it further says that the upper bound methodology is quite wide and it is applicable to most of them. You can even link the thermal aspect with this upper bound, because in all the cases we are calculating the 3 strain rates, 6 strain rates, and if we choose a material that has got a generalized stress in terms of the strain rate and temperature, one can use it for temperature as well as hot extrusion as well as. In fact, this work has been extended, and some work has already been published later, and very extensive experiment has been carried out to ensure the validity of this. So hopefully so now the upper bound chapter is over. With this, lot of cases we have taken, and you can practice. If there is any problem, you can mail me and we can answer you for your queries if it is so. There are still few more problems, popular problems, including slip line, upper bounds are left. We would take it up whenever there is a extra period. Probably maybe at the inside we would be taking those examples. However, the another topic, which is the finite element, which is again a simulation method. So the upper bound is a very popular simulation method, so far we discussed. The finite element method nowadays, it has become very popular because of its computational nature because of its applicability for any complicated shapes. So, in the next lecture we would be talking about the FEM concept, the finite element method, particularly specifically for metal forming. So, we would start simply, very simple, the advantage of finite element method to metal forming, and then we will extend it for 2-dimensional case, and then we would also extend it for the 3-dimensional case FEM, to show you that this basis of the mechanics and which is the main aim is to give you some modeling techniques. So, modeling technique today that is now staying is as the finite element method or finite element analysis. So, that requires detailed discussion, and maybe in remaining 6 lecture we would be discussing only on the finite element method. So, the finite element method, there are further different types of finite element method. We would be taking one by one, and at the end I once again thank you for your kind patience, but please do not forget to give your feedback about this lecture as well, and also the type of quality of talk and in terms of the video, audio and all those things. In the website, provision has been made to give marks for all these components at the scale of 5. You can mail me so that it will tell us how much more to improve. So, thank you very much.